Okay, welcome back. We'll do another example of finding local max and local min algebraically. So in this example, we'll start the same way as the previous examples. We'll take the derivative. We use the power rule. The 2/3 comes down, so we have 3 times 2/3 times x to the power of 2/3 minus 1, which gives you negative 1/3. We can simplify this. We have 2 over x to the power of 1/3. Now we've got to set the derivative to 0. 0 is equal to, so I'll say look for critical numbers from f prime of x equals 0 and f prime of x does not exist. So for the first one, f prime of x is equal to 0. That means 0 equals 2 over cube root of x, which is never. It's never going to happen. If you cross multiply, you're going to get 0 times the cube root of x is equal to 2, which means 0 is equal to 2, which is impossible. And f prime of x doesn't exist. That's going to happen. 2 over x to the power of 1/3 is undefined at x equals 0. So x equals 0 is our only critical point. But we have to check. Let's make sure we can plug it into the function. Check if x equals 0 is in the domain. So f of 0, that's 3 times 0 to the power of 2/3. Remember your exponent rules or exponent notation. This means take the cube root of 0 and then square it. Cube root of 0 is 0. 0 squared is 0. We have 3 times 0, which is 0. So it is not undefined. The derivative, or the original function exists there. So x equals 0 is in the domain of f of x. Thus, x equals 0 is a critical number. Okay, and the critical point would be 0, 0. Now we're going to make our number line. From minus infinity to infinity. We're cutting our number line at 0. I'm going to choose 2 test values. I'm going to choose, being strategic, I have to plug this in. I have to plug it into the derivative, so I'm going to choose a number that's easy to plug in. I'm going to choose -1. And I'm also going to choose, instead of being completely lazy and picking +1, I'm going to pick +8. Because it is arbitrary and I don't want you to get the impression that you have to always pick one to the right or one to the left. Now what we're going to do is we're going to plug them into the derivative, f prime at -1. So that's 2 over the cube root of -1. Now remember, square roots of negatives are not allowed, but cube roots are allowed. You can take the cube root of a negative number. A cube root of a negative number is asking what number multiplied by itself 3 times gives you whatever's in there. So what number multiplied by itself 3 times gives you -1? And the answer is -1. So 2 divided by -1, which is negative. So it's decreasing. On the interval from minus infinity to 0. We plug the other test value in, f prime of 8. That's 2 over the cube root of 8. What number multiplied by itself 3 times gives you +8? And the answer is +2. So we get 2 over 2, which is positive. So increasing. on the interval from 0 to infinity. That means that there's a max, or min rather. Thus, f of x has a local min at 0, 0. And just to highlight where everything came from, this y value, this y value came from evaluating the original function at 0. Okay. Okay, next example. I'm going to find the relative maximum of this one. So I'm going to take the derivative. Using the power rule for all the pieces. So the derivative of 2x cubed, we get 6x squared. Derivative of 3x squared, we get 6x. Derivative of negative 36x, we get negative 36. And the derivative of 9, we get 0. We're going to have to set this thing equal to 0 to find the critical numbers. And let's start on the right-hand side by common factoring a 6 out. So I'll have x squared minus x minus 6. And that's a quadratic. Factor it. X minus something, x plus something. We want mystery numbers that add together to give negative 1 and multiply together to give negative 6. And what will do that? Positive 2 and negative 3. We want all solutions to right-hand side giving us 0. So that's going to happen if 6 is equal to 0, which is never going to happen. 6 is always 6. It'll happen if the next piece, if the next part of the product is 0, so x minus 3. That part will be 0 if x is equal to 3. And then the last bracket, that will be equal to 0 if x is equal to negative 2. We have two critical numbers. We can tell right away that we can plug them in. Let's plug them in. Let's get the y values. At x equals 3, y is equal to f of 3, which is going to be 54 minus 27 minus, let's see, 108 plus 9. So that's going to be 27 plus 9, 36 minus 108. So negative 72, I guess. Okay, and then at x equals 2, or negative 2, y is equal to f of negative 2. So that's going to be 2 times negative 8, so negative 16, minus 3 times, so minus 12, then plus 72 plus 9, and then that's going to be so I'll subtract those. 60 minus 6 for 44 plus 9, 53. Oh, I've got to check this. Okay, then so we found the y values. Now we're making a number line. This is a polynomial, so our number line includes all the real numbers from minus infinity to infinity. We're going to cut that number line up at the two critical numbers that we found. So at -2 and at +3, again, make sure that you put them in from lowest to highest, put them in the correct order on the number line. Now we're going to have to choose some test values. We have 3 regions, so 3 different test values. I'm going to pick -4. I'm going to pick +1. I'm going to pick +5. Any number that's inside each of the regions will do. And then we're going to plug each of them into the first derivative. F prime at -4. I'm going to use the factored form of the first derivative. So 6 times -7 times -2, which is positive. Positive times negative is positive. So it's increasing in the first region. From minus infinity to -2. We have f prime at +1. That's going to be 6 times -2 times +3, which will be negative. So it's decreasing in the next region. On the interval from -2 to 3. I should have mentioned we didn't check where the derivative doesn't exist because there's no possible place where a polynomial doesn't exist. A polynomial can be evaluated at any x value. And then f prime at 5, that'll be 6 times 2 times 7, which is positive. That means it's increasing in the last interval. On the interval from 3 to infinity. And then we can do the interpretation step. Looking at the graph, there's a max at -2. Local max at the point -2, 53. And then there's a min at 3. Looks like the bottom of a valley. Local min at 3, -72. Just recycling the y values that we found already when we checked the domain. Okay, next example. This one gives us a hint. It tells us what the function is, which it has to, well, it doesn't have to actually. It tells us the function, it tells us the derivative of the function. It asks relative max, relative min. So f prime of x equals 0 means that x squared plus 9 over x squared minus 9 all squared is equal to 0. And we'd cross multiply. So x squared plus 9 is equal to 0 times x squared minus 9 all squared. And that means that x squared plus 9 is equal to 0. So multiply all that stuff by 0, it becomes 0. And that means that x squared is equal to -9. Now you tell me, is there a real number that you can square that will give you -9 or negative anything? Now when you square something, you take any number and square it, you're multiplying that number by itself. So if it starts positive, positive times positive, you're going to end up with positive. If it starts negative, you have negative times negative, that's also going to be positive. So this has no solution. Now we'll check. F prime of x does not exist because there's a division in the derivative. This is a potential location for a critical number. That means x squared plus 9 over x squared minus 9 all squared does not exist. And that means that x is equal to 3 or x is equal to -3. Either of those will cause the denominator to be 0. causes division by 0. But need to check if these are in the domain of f of x. Maybe they're in the domain, maybe they're not. So at x equals -3, y is equal to f of -3, which is -3 divided by -3 squared minus 9. So 3 divided by 9 minus 9, which is 3 divided by 0. So it's not in the domain. At x equals +3, y is equal to f of +3, which is -3 divided by 3 squared minus 9, which is also division by 0. 9 minus 9, -3 over 0, not in domain. So what does that mean? That means there's no critical numbers. No critical numbers, no critical points. So no local max, no local min. That's it. No local max, no local min. You may ask yourself, how is this possible? How does a function not have a local max and not have a local min? Well, a straight line is an example. A straight line doesn't have a local max or a local min. It's always increasing or it's always decreasing. This is not a straight line, however. It's a function that looks like this. It is, believe it or not, look at this. It's increasing here. The y value is going up there, and it's increasing, increasing, increasing. So increasing, 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 increasing. This function is always increasing. Look at the derivative. The derivative is always positive. You can't get a negative number out of that derivative. The top, x squared plus 9, two positive numbers added together. The bottom, something all squared. That's either 0 or it's positive. And it's 0 at the locations of the locations of vertical asymptotes. So examining the derivative carefully before we use it, just looking at it saying, well, that thing can't switch from positive to negative because it can't ever be negative in the first place. That's the fastest way to solve this. But we can go through the recipe, we can go through the method as indicated and find the same thing, that there's no max, no min. And we'll continue for the last three examples in the next video.